Welcome to For the Love of Go. If you're new to programming or just new to Go, you're in the right place. So let's get started. I'm going to show you how to build a simple calculator package in Go. And the first thing we're going to do is we're going to write a test, which might seem a bit weird. How can we write a test if we haven't done the thing yet? But this is the thing. Tests are absolutely fundamental to everything we do as software engineers. And writing the test is not some afterthought after we've done the code. It's actually part of the design process. So I'll show you what I mean. Let's go ahead and add a new file. Let's call this calculator test _test.go. So the name of the file already clues us in that it's a test file, and in fact that's meaningful to Go. So we'll find out how that works. Start with the keyword package and then the name of the package. This can be anything we want, but let's use calculator test as an example. So how do we write a test? Well, it's a function whose name starts with test. Let's try and add two numbers. That seems simple enough, doesn't it? So let's make this test add. And all tests take a parameter called t by convention, and they don't return anything. We'll find out what t is in a minute, but it's just the thing that allows you to control the test. So we always start tests this way. t.Parallel just tells Go that it's okay to run all of our tests in parallel. If we have multiple CPUs, which we probably do, we can run one test on each of them, which saves time. So the structure of a test is normally like we're going to call some function with some inputs, and we're going to look at what it gives us back, and we're going to check that it's what we expected. So in some ways, this sort of defines what it is we're saying the function should do, isn't it? So if we're adding two numbers, let's say we're going to add 2 and 2. So let's say what we want to get is 4. Let's call the function. It's going to be in the calculator package, so it's going to be calculator.something, and we've said it's called add. It takes two numbers, so let's give it 2 and 2. This is going to return something, the sum of 2 and 2, hopefully. So let's assign that to some variable got. So now we have want and got, and we want to see if they're the same, don't we? So we can write an if statement. So we can say if want is not equal to got, what then? Well, fail somehow. And the way we can fail the test is we can use the t, and we can call t.Errorf, which will give us some message, and we can say here's what I wanted, here's what I got. Now these percent markers, so t.Errorf takes a format string telling it how to format some data, and the percent sign's a little placeholder saying data goes here. So we're going to print out, so suppose we got 5 by mistake, and we're going to print out want 4, got 5. So we'll see what happens. If they are the same, then there's nothing else we need to do, because tests pass by default unless we explicitly fail them. So that's all we need to do. So the compiler's complaining because I haven't imported the testing package. So if I save the file, that'll auto-create the import statement for me, so that's good. This bit's not so easy to fix because it's saying I don't know about a package called calculator. We can fix this by importing it, but it still doesn't actually exist yet, of course, but that's okay, we'll get there. So now the red line's gone from here because it knows where calculator's coming from. I've imported it. But now the import statement is complaining because, well, the package doesn't exist yet. So let's first of all create it. So we can run go.mod init calculator, which means dear Go, please initialize a new module whose name is calculator. And for now we can think of a module as being the same as a package. Here's the go.mod file that gets created. It just says module calculator. It's like saying, hey Go, in this folder is where the calculator package lives. So that's helpful. So does this work yet? No, because it's found the calculator module all right, but it didn't find any calculator package within it. How could we create that package? Well, we actually already did that when we created package calculator test. So let's do that. Package calculator, thank you. How are we doing now? Not bad. The import works, but we still have a problem here, because even though we now successfully found the calculator module and imported the calculator package, there's no add function in that package, which makes sense because we didn't write that yet. So let's go ahead and write it. Let's go split screen so that we can see the test and the code at the same time. So what do we need to do? We need to define an add function, don't we? So that's func add. No thinking required here because we already chose the name as we were writing the test. That's part of the design process we were talking about. And we've said it takes 2 parameters. And these are, let's make them floating point numbers. We could use whole numbers, but it's more useful calculator if we can work with fractions, right? So let's do that. So let's call them A and B, and we'll give their type as float64. That's the name of the Go type for fractional values. And we're also going to return some value, also float64. Great. Here comes the function. Well, we're not actually going to finish writing the function yet, because what I want to do is, first of all, I want to get the test to compile successfully. That's a good start, isn't it? You need your program to compile before you can start running it. And the simplest way I can do that is by just returning anything at all, let's say 0. Obviously I know that's not correct, but it'll make the compiler happy, because the compiler knows nothing about what this function is supposed to do. It only knows that I promised to return a float64 value, and we can ignore the error from the linter asking for a comment. Haven't finished completely designing and implementing the function yet, so when I've done that, it'd be a good time to write documentation. How are we doing on the test? So is it compiling? Not quite. We have an error. Cannot compare want and got, mismatched types int and float64. Why is that? Well, we know what type got must be. The compiler can work that out too, because it knows what type calculator.add returns. It's a float64. If we want to compare something with a float64, we'd better have a float64, hadn't we? So we've set up want here, and we've said it's for. We didn't say what type this variable should be, so the compiler's going to try and infer it. And quite sensibly, it's inferred that I want an integer variable, because this is an integer number. So let's make this, let's use var, so when we define a variable with var, we can give its type. And now there's no problem with inference, because want and got are the same thing. So we actually have the test compiling. Let's try and run go test and see what happens. We don't think this should pass yet, do we? I mean, we know that the implementation of add is not quite right. We'll fix that, but why would I want to run the test now? Well, for one thing, I know what I expect to happen, which is that I think this test should fail, and I think I know exactly why it's going to fail, which is that it's going to say want 4 got 0, right? If that's what happens, then great, all my assumptions are correct, so I understand what the program is doing, and that's a good place to be in if I want to continue developing it. If it turns out I got something wrong and it behaves some different way, well, I need to figure out what's wrong with my expectations before continuing, so let's find out. Okay, that looks pretty much like what we expected, doesn't it? So let's just take a closer look at this output. So I ran go test in this folder where the calculator package exists. So what does go do then? How does it know what tests to run or what to do? What it does is, it first of all looks for some files whose names end in _test. That's important. If they don't have that name, it won't find any tests. Having found some of those files, hopefully, it then looks in that file to see, are there any functions whose name starts with the word test? So test is a magic word in this sense. If I named this function something else, bogus add, now it's not actually a test, and if I run go test, nothing will happen. No tests to run. So that's how that magic works. So if you ever find that your test is not, Go doesn't seem to recognize that there is a test there, just check. Firstly, the file name should end in _test, and then check that your test function starts with the word test. Brilliant. So the test is failing. That's actually quite important, because suppose I'd just gone ahead and finished writing add and then I ran the test and it passed. Would I be done? Not quite, because I actually haven't tested the test. You know, I have some logic here which is supposed to behave in a certain way, and I haven't checked that it does. I could have got the same result by just not writing anything at all here. You know, this passes because it doesn't fail. So, I mean, it's reasonably easy for us to look at this and see that's a bogus test, but there are ways to accidentally pass tests which are less obvious than this, so let's undo that. So what I'm really interested in doing is saying, does the test work? By which I mean, if my expectations about the function are not correct, do I see the message that I expect to see? Is it the right message? Does it contain the right data? Is it helpful information about what's gone wrong? It is in some senses. So for example, it tells us here that it's failed. That's important to know. If everything passes, then there's no output at all except the word pass, as you've seen. It tells us which test it was that failed. That's useful to know too. It also tells us the precise file and line where the failure was. So calculator test, line 13, that's here. Makes sense, doesn't it? Because that's the call to t.Errorf. So for whatever reason the test failed, it would be bound to be at this line. And we can see want and got, but imagine I'm not looking at the code here and I'm just looking at my failure output. I'm kind of like, want 4 got 0, okay, but under what circumstances? You know, what were your inputs, for example, that would lead you to expect 4 as the answer? So let's put those as well. So let's say something like add with x and y, and then I'll say what I want and what I got. So should we make this a and b here? And then I can use those variables again. Let's say a and b are float 64. A is 2, b is 2, and here's the output. Okay. This should still fail, but hopefully we'll see a little more information. Alright, so this looks pretty good. Add 2 and 2, want 4, got 0, and in fact we're seeing a few more decimal points than we really need, aren't we? So let's limit that. So this instruction in the format string says just print 1 decimal place after the decimal point. Don't give me too much information. How's that looking? Great. That looks much nicer, doesn't it? So now we have a really informative test output. If I were to, if I go on and finish the rest of the calculator package and then I make some change at some point in the future which actually breaks add, so it stops working the way it's supposed to, all of a sudden my test, which was presumably passing before, will suddenly go to failing, and I'll have all the information I need here to dive in and start seeing why that might be. So that was a fairly involved process. So are we nearly done? We're nearly done, because the only thing left is basically to make this pass, isn't it? And that's pretty easy. This should work. Let's find out. Yeah, it does, which makes sense, doesn't it? Because 2 plus 2 should equal 4, assuming everything's behaving as we expect. So that's really nice. So we've done that. So now it's your turn. Over to you. Hopefully you've got Go installed and some kind of editor. You can use VS Code if you like. Other editors are available. Just set up the test and the code in the same way that we've done here. Just review the video if you need to. And run the tests when you get to this point and just check that everything works for you. If not, just double check the code and make sure that you're on the same page as me. So pause the video now and have a go. Welcome back. Did it work? I hope so, because we're going to go ahead and do a bit more now. Let's try and do subtract. So we'll do it in the exact same way. Now you know that we're going to start with a test. It's going to be pretty similar to test add, isn't it? So let's just copy and paste test add. Let's turn it into test subtract. What else needs to change? This is fine, these are fine. Our want is going to be different, because 2 minus 2 should be 0. Because we're calling a different function, we can change that. And we'll change this message. So right now, we're in the same place that we were with test add, which is subtract not declared yet. So we can declare it. Same signature, it takes A and B, which are float 64s, returns a float 64. And again, I'm just going to deliberately write a broken version of subtract, just so I can get everything to compile. I want to run the test and make sure that it fails in the right way. It doesn't. So why is that? Well, it's because I expected 0. So that's on me, really. I should have chosen a better set of test inputs, shouldn't I? I should have chosen something which wouldn't pass if the function returns 0, because I know that's how I'm going to start implementing it. So let's say 3 minus 2 should equal 1. Right. This definitely won't pass. Let's just make sure. Great. That's more like it. So here's the message. Subtract 3 and 2. So subtract 2 from 3. I want 1, got 0. Great. Now I can make it pass. That should be all right. Let's have a look. Yeah, looks pretty good, doesn't it? So let's do multiply in the same way. This should be straightforward. You should have no problem with this whatsoever, and I'll get you to do the same steps in a moment. What do we need to do here? Let's keep the same A and B, and let's say 3 times 2 should equal 6. All right, let's define multiply. Float 64s, returns a float 64, and I'm going to return 0 as usual. Now I can verify my test if you like, just to make sure that it fails the expected way, and it does, which is great. Now I can make it pass. Fine. Now it should pass. Excellent. We're in good shape. So as before, go ahead and add in the code for test subtract and test multiply in the same way that I've done. See if you can do it without referring to the video. So pause the video now and have a go. All right, how did you get on? So we would like to do the remaining operation, which is test divide. But before we do that, let's just see if we can refactor these tests to be a little bit better. So something you'll notice about test add, for example, is that it basically only tests one set of inputs, doesn't it? So if we've written calculator.add correctly, which I think we have, then one set of, if it works for one set of inputs, should work for them all, but it's possible to imagine that we got that wrong, isn't it? If it was a more complicated function, for example, there might be different ways it could behave depending on what inputs we gave it. So how could we give it different inputs? Well, one option is we could just write a new test, couldn't we? We could just say test add something else and have the exact same code, with the only difference being the values of a, b, and want. That's all right, but it's not great. And if you wanted to write lots of cases, it would be very verbose and not that much fun to write. So let's see if we can work out how to test multiple sets of inputs in the same function. How could we do that? Well, instead of just a and b, suppose we had what we really want to do is we want to have a set of a, b, and want. We want multiple sets of those, any number we want. So we can use something called a struct, which is effectively a record type in Go, so we can group a set of variables together. It would look something like this. We define the names of the fields, which are the pieces of data inside the struct, and we give their types in just the same way that we declared a variable with var, you'll notice. But we say struct instead. So this is some type. Let's call it test case. So the keyword type introduces a new type definition. Here's the name of the type, and here's the definition. We understand this. So what I'm going to do is I'm going to define a slice of these test cases. So we can think of that as an array if you're not familiar with slices. It's basically a collection of the same type of data. So let's call this variable TCs for test cases. And we're going to say it's a slice, so these square brackets mean here comes a slice of something. A slice of what? Well, a slice of test cases, that's fine. And now curly brackets to say, here it is, here's the data. So how do we write that data? Well, we write what's called a struct literal, which is to say, you know, it's literally this data. We're going to give the data that we want. So curly braces, and then the name of the field we want to set, colon, and some value. So let's use the same case that we already had. 2 and 2 makes 4. Fine. Trailing comma after each struct element, after each slice element, that's fine. So now the compiler says, okay, you declared TCs, but you never actually used it. That's all right, we're going to. So cool your jets, compiler. We're going to get there. What can we do with this slice of test cases? I know it's only one at the moment, but we could add more. So we're going to loop over it. So it's easy to write loops in Go because there's only one keyword, which is for, and then we can use the range statement to range over it. So we're going to say for TC equals range TCs. So I'll break this down a bit. So first of all, for, you know, introduces a loop. And then range takes some collection of things, a slice for example, a slice of test cases in our example, and it runs whatever's inside the loop body once for each thing in TCs. That makes sense, doesn't it? So inside the loop we're going to need the name of the element that we want to look at, the name of the particular test case. So that's going to be TC here. This other thing, range returns two values. It returns the index number of each element, so 0, 1, 2, 3, etc. The position indicator within the slice. But we don't need that, so we've just ignored that using this underscore. That's called the blank identifier. So this is a very common loop structure to see in Go. We call it ranging over a slice, and each time round the loop, TC is going to be our test case. So we actually kind of already have the code that we need, so we can just move it inside the loop. And now instead of A, it's tc.A. That's how we reference a field in a struct. Same thing here, tc.B, tc.want. That's all right, same thing here. Great. So we sort of feel like this should still pass, don't we? Because the test data is the same. All we've done is refactor this to be much longer and more complicated than it was for no apparent benefit. But we'll see why it's worth doing this now, because we can add more cases, of course. Sorry, 3 and 3 makes 6. That should still pass. Great. This is looking all right, isn't it? And we can see, let's do something like -2 and -2. So -2 plus -2 is the same as -2 -2, so it should be -4. I think that's right. Good, yeah, that's encouraging. Let's do another one. So let's do -2 plus 4 equals +2. Great. That's looking very nice, isn't it? So what does it look like if it fails? Well, we can find out by just, let's deliberately make this wrong, and we'll run the test again. And we'll see what it looks like. Fine, that's what it looks like. You saw this already. 1, 3, got 2, and you can see that I'm showing my inputs here, which is really helpful. So that's nice. So, okay, you go ahead and add some test cases to your package now. You don't have to use the same ones. In fact, try and choose some interestingly different ones. Perhaps big numbers, small numbers, negative numbers, positive numbers, zeros. You get the idea. 4 or 5 test cases is probably good. Of course, we could have lots more, but something like add probably doesn't really need them. So go ahead and try that now. Pause the video and have a go. All right, welcome back. So we have multiple test cases for add. That's really good. And we could go ahead and add the same for subtract and multiply. But let's do something a little more interesting. So suppose we said all of the test cases for all of these functions are going to look somewhat the same, aren't they? Like we have 2 float64 inputs and 1 float64 output. It almost seems like we could test all 3 functions in one test, doesn't it? Could we do that? Well, what would we need? What we'd need is some way to specify which function we want to call, right? So we would need to be able to say this is an add test case rather than anything else. So how can we do that? Well, we're going to need to add some field to our struct. Let's call it fn for function. It's the function we're going to call. You can have variables or struct fields which are functions in Go. That's perfectly all right. But how do we spell the type of that function? The answer is it's the func keyword again. We're telling Go this is some kind of function. And we give its parameters and returns in the same sort of way that we do when we define the function. They don't need names because we're not going to use those names. We just need to tell it what types. So fn is a field which stores a value which is some function that takes 2 float64s and returns a float64. If we've done this right, then we should be able to set this to the function we're interested in, which is calculator.add. Good, that works. Let's just update the rest of these. Fine, but I need to actually use that information somehow, because right now we're calling calculator.add regardless. So that's actually quite easy because it's just tc.fn. You know, every time around the loop, tc.fn will be some function. In this case, it's add. We'll call add with the inputs, and we'll check the results. So this should still pass, shouldn't it? No. So add 2 and 4, want 3, add -2 and 4, want 3, got 2. That's okay. That's a deliberate mistake I put in to check you're paying attention. Excellent. So we're all done. So here's a bit more of a challenge for you now. Go ahead and make the same change to your code, but I want you to also put in some test cases for subtract and multiply. So at the end you should have one test, let's call it test add sub mul, which has a few test cases for each of these three functions, and just check that that all works for you and that passes. So pause the video and have a go. Alright, welcome back. I'm not going to do the same here as you've already done because I'm sure you had no trouble with it. Let's go ahead and think about divide now. So why have I left divide to last? One interesting thing about divide is it's maybe slightly different to these other functions in that you can... Not every pair of numbers is a valid division, right? You can't divide things by 0, for example. Or, you know, in straightforward everyday arithmetic, we don't allow people to divide by 0. If you try this on your old school electronic calculator, it will give you some kind of error message, or complain in some way, or explode. Be careful when you try this. So we need to have some way to make our function behave a bit like that, don't we? So, as before, let's start by writing the test, and then that will effectively define the behavior we want, and then we'll see how to do it. So let's call this test divide. t.Parallel, fine. A and B, fine. We won't worry about test cases for the moment because we just want to get one case working, and then we can worry about adding some more. So let's do a nice easy division. Let's say 3 divided by 3 equals 1. Right, this is reasonable. So first of all, we're just doing the easiest thing, which is a valid division, if you want to call it that. So let's implement that the simple way. We know we're going to need more than this at some point, so let's just return 0 for now so we can check the test. Fine, it's failing the way we want. So now we'll do the simple implementation. This is all right. That should pass, and it does. Okay, let's step up the difficulty now. So let's try an invalid division. So let's say 3 divided by 0, we don't want it to be 1, we know it won't be. It'll be something else. Let's find out. So this is what Go itself does, you know, the division operator in Go. If you divide something by 0, what you get is a value called +inf, i.e. that's positive infinity. Which makes sense from one point of view. But we're saying for our simple calculator, we don't want to deal with things like infinity. We just want to be able to say, sorry, you know, that's not allowed. Invalid operation. Please try again using some different number. Literally anything other than 0. So how could we do that? We're going to need some code which says, is this second argument 0? If so, uh-oh, problem. What can we do? We need to signal to the user, the person calling divide. We need to tell them, hey, you did something wrong, that's not allowed. We can explain what it was they got wrong and how to fix it. But how do we send that message? So we could, one obvious way to do it is by this return value, isn't it? So we could say we're going to agree amongst ourselves that a certain special value here means error, like we could say 0 or -999, or any arbitrary number that you care to come up with. We can agree that convention. That's how it's going to work. But there are a few problems with this. It's not ideal for various reasons. It's often hard to choose what's called an outer band value like this, because if we use 0 for divide, but then we couldn't use that for something else. So we'd want it to always be the same value. And we have the problem that you just have to know. That's what this special magic value means. And you can check it and say, did I get that magic value that means error? This is not very satisfactory. Actually, what we'd like to do is leave this value alone altogether and have this always be, let's call it the data value, the result of the division. And we'd like some other value which tells us whether or not everything was okay. You could think of it as a kind of a flag, a signal saying, hey, something's gone wrong, or everything's fine, perfectly valid division. So we can do that in Go because functions can return more than one thing. This is very useful. In fact, what Go functions almost always return is exactly this, some kind of data value plus some what's called an error value. The error value can be nil, which means no error, naturally enough. And if it's not nil, then it could be something else, and there's actually an error type in Go which we can use to give some information about what went wrong. So let's see what that would look like from the point of view of the test. We're saying, so right now, if we look at this line, we have an assignment statement, which is this colon equals part. We have something on the right, which is the value returned from calculated divide. We have something on the left, which is a variable to stash that value into. We're saying now calculated divide is going to return two values. So there's going to be two things on the right-hand side of the assignment. We need two things on the left, don't we, to counterbalance it. So if your function returns two values, you need two variables to store them in. So it's conventionally called err, as in error. And let's say, so compiler's angry right now because we haven't made that change yet, but let's just proceed, assuming that we have. So what's next? So we received this error value. Clearly we need to do something with it. I'm sure you're way ahead of me. We need to look at it and say, is it nil or not? If it's not nil, that means some error happened. That's the semantics we're going to agree on. So we can say, and actually right now, I'm saying with these inputs, I should get an error, shouldn't I? If I try to divide by 0, the error should not be nil. So I actually want to fail the test if it is nil. Seems a bit backwards, but I'm just going to say, so if is nil, then fail, because with divide, let's just say divide by 0, want error, got nil. Fine. So I don't have any data that I need to print out, so I don't need errorf. It's just error. So if we get past this bit, then we know the error was not nil, or we would have failed. So what does a non-nil error mean? Well, something went wrong. So in that situation, what do we do with the data value? Well, the answer is nothing, because if there's an error, then it's sort of saying I wasn't able to do that division for you, so sorry, can't help on this occasion. So we could compare it with something, but what? I mean, it's going to be wrong regardless by definition, so there's really no point looking at it. And in fact, if error is not nil, then we're saying don't look at the other value. It's not valid. So we would like to say, you know, if error is nil, and we won't get to this point because we will have failed, but we're saying don't even look at want and got unless the error is nil, and we're saying we expect that it will be. So let's get this compiling first of all, usual procedure. So right now, the compiler is angry because cannot initialize two variables with one values. So we've got two variables here, one value here, something doesn't balance. We need to get divide to return two values. Let's do it. Here's where it would go, because we return not just a float64 now, but a float64 and something else. What else? Well, it's an error. We need parentheses around here now because we have two things. Fine, now return is angry because we didn't return enough things that we promised to return. Let's return just nil for now. So we don't expect the test to pass because it's requiring us to return something non-nil, but let's just check. Fine, so it is failing. And let's just update this. So first of all, we're getting divide by 0, one error, got nil. That makes perfect sense because we returned nil, even though we knew we shouldn't. That's all right. And then we have this failing because the error is nil, and now we're comparing want and got, which is wrong. So there's something wrong here, isn't there? We shouldn't get two failures. What's failing is that we should have got a non-nil error, but we didn't, and that's it. That's what's wrong. So we would like to say here, for example, not only do we need to fail the test, but we also need to not go on and do anything else. So we need to just bail out of the test completely. It's a catastrophe. There's nothing more we can do. We need to stop short on the whole thing. So that's what t.Fatal does. t.Fatal, as the name sort of suggests, it's like the failure is so bad, it's worse than t.Error. It means we need to short circuit all the other things that happen in this test. So that's what t.Fatal does. So now we just get the one failure, which is what we wanted. Can we make this pass? Let's have a go. So we're saying, so what needs to be different here? What the test is asking is if b is 0, that is if the second value is 0, then we should return something other than nil. So we can write that. So if b is 0, return something, don't know what, but we'll come back to that. And this doesn't want to be nil. So literally anything other than nil will pass the test. What we can do is we can use errors.new to construct a new error value. And it takes a string, which lets us give some helpful information to the poor old programmer who's not sure why this has failed. So we can convey that information here. We'll just say division by 0 not allowed. That's not required for the test because we don't check for the specific string or anything. All the test is interested in is, was it not nil? Which is what matters. And the rest is sort of human level information. So that's the error value. What about the data value? Well, it really doesn't matter, does it? Because the semantics of a non-nil error means don't look at the other value. So it can be anything, and in fact the convention is just to return 0. But like I say, it doesn't matter. So now that's compiling. This is compiling. Is it passing? Yes. That's really good. So we would like to... We've only really tested half of the required behavior, haven't we? Because we're just testing that we get a non-nil error. We didn't actually test any divisions, so we would like to do that. So again, let's set up some test cases. So we don't need to define a named test case type. We can just use what's called an anonymous struct, which is just exactly the same, but we just give the struct definition instead of first defining it and then using the name. So as before, A and B, float64, want. And there's something else, isn't there? Because we'd like to be able to say, we'd like some valid test cases in the sense that they're divisions you can do, and we'd like some invalid ones in that they're ones which produce an error. So how could we express that? We could say, like, it sounds like a Boolean variable, doesn't it? Like it's either okay or not okay. Let's call it error expected and make it Boolean. So what this means is, if this is true, then we do expect an error for this test case, which means we're going to be dividing by 0. Or if it's false, it's saying this test case should not produce an error. If it does, that probably indicates a bug. So that's the definition. Here is the test case we have right now, which is A is 3, B is 0. Want doesn't matter because we're not going to be looking at it. So a good tip here is to use something unlikely, let's say 999, so that if we do see that value in our test failure, we know something kind of went wrong with the test at some point, because we shouldn't be comparing that. Assuming we did get the expected error, we shouldn't be looking at want. So if we see want in our output, something's wrong. That's why I use a crazy value. And we know error expected is true for this one. So fine, that's easy. We'll just finish this refactoring. So again, we're going to write a for loop ranging over TCs. Each time through, TC is the test case. This is going to be TC A and B. That's TC want. And the same thing here. So how's it looking? So this is compiling. Will it pass? I feel like I expect it to. It's just the same test data that we already had, but in a needlessly long-winded form. So let's find out. Yep, it's all good. Okay, now here's the payoff. So now let's do a non-error one. So 3 by 3. We want 1. We need to set that in this case, and we're saying error expected is false. Let's have a go. That is failing. So divide by 0, want error, got nil. Okay, why is that? Let's have a look. One problem is that we don't know which test case this is. We can guess, but let's make it explicit. So let's, again, say what our inputs were in abbreviated form. Now that's F, because we have a format string plus some data, TC A and B, and that's it. Now let's see what that looks like. We should see which test case it was, shouldn't we? It was 3 divided by 3. Well, that's interesting. Let's look closer. So 3 divided by 3, want error. That immediately makes me suspicious, because I don't think we do want an error. So do we need to tweak this test code a little bit? I think we do. So I think this is the problem. So we're saying we're always failing if error is nil, regardless, right? We're not even looking at error expected, so that must be wrong. So this needs a little more sophistication now. We need to say something like, if error expected then we want an error, and if we didn't get one, we should fail, or if not error expected and we did get an error, we should fail. So rather than write two separate failures, let's suppose we construct, we have a boolean, so let's make another boolean to compare it with. Suppose we had some variable error received, which is true if we received an error. So that's easy to write. We already know that. So we're saying if error is not nil, this variable is true, i.e. there was an error. If error is nil, there was no error, so this is false. So now we can say if error received is not equal to tc error expected, this needs a little bit of thought maybe, but it does make sense. So we're saying if either we didn't expect an error and we didn't get one, or we did expect an error and we did get one, in either case that's fine. So the only thing we really care about is, was there a mismatch between the error status that we expected, controlled by this, and the error status that we actually got, controlled by this. So what we're saying is unexpected error status, right? Either that it should be there but it wasn't, or it wasn't there, or it shouldn't be there and it was. And we're going to give the error itself. So we can just use %v here. So %v prints out any value of any type. And here's the error. So what should we see now? For this test case, which was failing, so we think error is nil. So error received is false. So this is false. What's error expected? That's false. So these things are equal. So this if statement is not true. So we won't fail here. So we will go on to this line. So let's just see what this does. Okay, that's passing. So we can, another way to say this is say, if we didn't expect the error, this makes no difference to the behavior because we already verified here that we both received, or we expected and received an error, or not. So the only time we're interested in comparing want and got is in the non-expected error situation. So that's great. This should still pass. Now that's failing. Okay. Divide 3 by 0. I want 999. So here's that crazy value that we said we should never see. We are seeing it. So clearly I got the test wrong. Let's take a look at why. This is being executed precisely when it shouldn't be, and that means one of these must have the wrong sense, and it's this one. So I'm saying I want to say, only move on to this comparison if we're in a non-error expected situation. So does that fix it? Yes, it does. So that looks nice. So this is a tiny bit complicated. So if you're feeling confused, don't worry. Let's just go over this one more time and break it down. So it's a test. We're running it in parallel. Here's the definition of our test case struct. This is what we're going to supply for each test case. Here are some test cases. Here's the first one. 3 divided by 3 should equal 1, and there should be no error. Here's the second one. 3 divided by 0, we don't care about the want value, and we do expect an error. Now let's use those test cases. So we'll create a loop which iterates over them. Each time through, we're going to call calculator.divide with a and b from our test case. We're going to record what we got and any error value. Then we're going to say, did we receive an error, i.e. was that error value nil or not? We're going to compare that against the error status that we expected to have, yes or no. If there's a mismatch, then we should fail, either because there was an error when there shouldn't have been, or there wasn't one when there should have been. And providing that status is okay, we'll get past that. And we're saying, for valid test cases only, i.e. for all of those test cases where we don't expect error, let's compare once and got. And we do. So let's double check what we've done by tweaking our test data so that it's deliberately wrong. So let's say, suppose for this valid division we expect an error. So this should definitely fail, shouldn't it? If it doesn't, there's a problem, but let's try. Yeah, it fails. Let's see why. Unexpected error status, nil. That kind of makes sense, doesn't it? Because we're saying for 3 and 3 we expect an error. We don't really, but this is a fake to see what the test does. We expected an error, and what we in fact got was nil. So as it happens, the divide function is correct, and it's our test data that's broken, but that's okay, we're just having fun. So we'll fix that. So let's try the opposite situation, which is for a case where we do expect an error, let's give it some valid data. So let's give it 3 divided by 1, for example. That should also fail. Right. 3 divided by 1, unexpected error status, nil. Again, that makes sense, doesn't it? Because we know the function is correct. This is a valid input, so it's going to not give us an error, but the test says that it should. So again, we have unexpected error status. Now let's restore that, and then let's add one more case where we get the opposite unexpected error status, i.e. we get one when we didn't expect one. So you can do, let's say, 10 divided by 0. That should fail. And it does. So now the failure is divide 10 by 0, unexpected error status, division by 0 not allowed. So remember, that's the string that we defined as the error value with errors.new in the code. So we're saying the fact that we're seeing this message means we expected the error to be nil, but here's what it actually was: division by 0 not allowed. So I hope that makes sense. This looks a little bit complicated, but in fact this kind of pattern will work for pretty much any Go test. So you're going to have some multiple test cases probably with different types of inputs, different expectations about what should happen. List some cases, range over the cases in a loop, calling the function, checking what it returns against our expectations. And this idea will work for basically anything. And since lots of functions, as we were saying, return something and error, this logic is going to be just right for testing those as well. So once you've successfully written this test, you can use it as a pattern for most of the tests that you'll write in the future. So I think that's a nice place to leave it for part 1. Go ahead and update your code to do this error handling with divide, and I'll see you in part 2.